interact at some point during their lifetime, so exchange of mass, maybe they'll go through a common envelope. So to kind of clarify my previous point, we know massive binary stars are important because when we talk about massive stars, we have to talk about massive binary stars. The binarity of these systems kind of complicates the picture of our understanding of massive stars. I'm showing here another cartoon depicting binary stellar evolution. So this is showing one possible life cycle for a massive stellar binary, starting with two massive stars on the zero-age main sequence. They go through multiple mass transfer events. Because they're both massive stars, each can undergo a supernova. This system passes through a common envelope and eventually reaches a binary neutron star system that will merge to produce a black hole. And so as my title suggests, I study one particular phase of this process, the high mass X-ray binary phase. So to give a little bit more detail, a quick overview. So high mass X-ray binaries are systems in which a black hole or neutron star is accreting from a high mass stellar companion. And to kind of talk about how we go about observing these systems, when we're looking at the black hole or the neutron star, we need to kind of look in different wavelength regimes because of the physics of how they emit their photons. So when we're talking about the accreting compact object, we study those through X-ray emission at quote-unquote softer X-rays, so less than 10 keV photons. In my work specifically, I used the Chandra X-ray Observatory, and the real key for this is that because of Chandra's high angular resolution, we can obtain really precise positions for these X-ray binary systems. We can layer on harder X-ray observations using NuSTAR, which observes at greater than 10, which allows us to observe greater than 10 keV, which can start to allow us to distinguish between black hole and neutron star systems. And then turning to the companion stars, we use optical, infrared, and UV emission. In my work particularly, I've been focusing on data from the Hubble Space Telescope, which allows us to both study to identify and study these companion stars and place them in the context of their parent stellar populations. Another motivating reason for studying massive binary stars is that we know that these systems, a lot of people are excited about kind of the last two panels of this cartoon of their evolutionary picture. So when you have a binary neutron star merger forming a black hole, you can get gravitational waves coming out. And we are still in the process of really understanding this population of compact object mergers that are now being observed with gravitational waves. And we know that isolated binary evolution plays some role in this picture, but we're still kind of deciding as a community kind of what types of formation channels are contributing what fraction to this population. We know that there's also a contribution from other processes like dynamical evolution in dense stellar environments. And then kind of the last piece here, in terms of a more cosmological view, high mass X-ray binaries are also important because they're a likely contributor to cosmic reionization at redshifts kind of beyond about 5, as you can see on this graph. HMXBs dominate as kind of the production of ionizing photons in the universe. So to kind of quickly sum up my kind of background and motivation, we know that massive stars play an important role in galaxies. Their evolution is pretty complicated when we have to involve this binary interaction. They're progenitors to binary compact object mergers observable with gravitational waves, and they also likely played a key role in the production of ionizing photons for reionization. So kind of motivation and background aside, how do we actually go about kind of using HMXBs to answer these types of questions? There's kind of two approaches. There's several different ways you can go about this. So you can study integrated X-ray emission from more distant galaxies, looking at how kind of the X-ray luminosity of these systems scales with galaxy-wide parameters like star formation rate, stellar mass, metallicity. You can do detailed studies of individual systems in the Milky Way, which allows you to do kind of more detailed accretion physics type studies. And the work that I do kind of lies somewhere in between. So when we look at nearby galaxies, we can do these population studies of high mass X-ray binaries. So we get a more detailed view than we do using the integrated X-ray emission from more distant galaxies, because we can actually identify individual systems, identify their companion stars, but we can't get kind of quite as detailed for each system as we can in the local Milky Way systems. So why is this, local group galaxies are a great place to do this kind of work because they're close enough that we can actually resolve their stellar populations. So I'm praying that this movie will work, okay? So this is a video that is part of the FAT survey, which I'll talk about more in a second, of Andromeda M31, and just kind of showing so kind of going from, you can see the scale of Andromeda here, and we're going to zoom in to a part of the disk to kind of show what type of observational data we're working with here. And it's very exciting because you can see it just keeps zooming in until we can resolve all of these individual stars in Andromeda. And so this is a massive HST survey, the Panchromatic Hubble Andromeda Treasury, which provided individual photometry for over 100 million individual stars in Andromeda. And so this is the observational data on the optical side that I use to study HMXBs in that galaxy.
Margaret, can you remind us of the order of magnitude, the number of high-mass X-ray binaries in the Milky Way that we can observe, at least? Yeah.
I think for high-mass X-ray binaries, there's like, I would say, I think roughly 100 is the order of magnitude of kind of the systems that we know about. So local group galaxies, because we have these resolved stellar populations, we have a whole system of high-mass X-ray binaries at the same distance, which kind of alleviates some of the issues with observing these systems in the Milky Way, where you're looking through the disk of our own galaxy. And these local group galaxies also span an interesting range of metallicity and star formation rate intensity to kind of allow us to probe different stellar environments in which these systems formed. So I'm showing here a mosaic of the FAT survey footprint in M31, and just to kind of show how we can kind of go from this picture and then how close in we can zoom. So this is kind of the scale of the zoom in that we do to identify high mass X-ray binary companion stars. So we're zooming into a roughly 40 by 40 parsec region of that galaxy. So I mentioned resolved stellar populations. So with that, to just kind of clarify, what we can do is we can actually identify and characterize the companion stars in the HMXB systems. And we can also determine the ages and calculate HMXB production rates using star formation history, spatially resolved star formation history maps, which are something that we can create with these resolved stellar populations observations. Okay, so I'm going to now kind of jump a little bit more into these HMXB populations in M31 and M33. So these are the galaxies that I've focused on in my work. They're the two closest spiral galaxies to the Milky Way. They're both at a kind of comparable distance, which is kind of great. So we can use a very kind of analogous observing strategy for both of them. And so on the left, you can see, use this stick, I guess. So this is that FAT survey mosaic that I showed before, and kind of overlaid on a bigger picture of M31. So this is the region that I focus on in M31 in my work. And then on the right here is the analogous HST survey of M33, which is named FATTER. And so that's the mosaic from that data set as well. And just kind of an aside here, one thing that's exciting is that we have new HST survey called FAST of the southern half of Andromeda the data is currently rolling in. So that'll be exciting to kind of allow us to double the area of the galaxy that we've been able to do this work. So M31 and M33, besides being kind of the closest spiral galaxies, which kind of makes them an obvious choice for this type of work, they're also interesting because they span a wide range of star formation rate intensity and metallicity. So you can see M33 reaches higher star formation rate intensities than M31, which is great when you're studying massive star populations. You want to have a lot of kind of ongoing star formation. And in terms of metallicity, it fills in this gap in kind of the local group metallicity space between M31 and the Magellanic Clouds. And it has M33 has an interesting kind of metallicity gradient through the disk. So just a quick overview of the kind of multi-wavelength coverage that we have in these galaxies. So on the left, I'm showing a near UV image of M31 with the footprints of the Hubble, Chandra, and NuSTAR data that we have in that galaxy. And on the right, showing the same outlines for our M33 observations with the HST survey, Chandra in cyan, and then NuSTAR in green. And just, for people who might want to look up the specific data sets that I'm using. So in M31, we're using the FAT survey, which is the Panchromatic Hubble Andromeda Treasury, the Chandra FAT survey, which is a Chandra survey designed to overlap with FAT, and then the NuSTAR M31 legacy survey, which kind of covers the bulge and then part of the disk. Yeah.
For M31 and actually M33 as well, do we have an idea of the recent star formation history, sort of a more resolved version of it over the last 50 million years or 30 million years? Because I think that's at least one of the conjectures that has been made by Serena and Chiguera, for example, for the overabundance of BH2 binaries in the SMC, is that there was this burst of star formation right around 30 million years ago, which is just prime time for seeing the BH2 binaries today.
Yes.
So it's you know, like whether if it's bursty, then in the regions of interest, it could be more relevant than the overall average star formation rate.
Yeah, so we do. We have spatially resolved recent star formation histories for both galaxies that come from these HST surveys. So in M31, that's what I used the maps. They were led by Alexia Lewis, and then I actually created the maps myself for M33. So we study the star formation kind of back to about 500 million years ago, but with pretty close resolution in the younger age bins. So then in M33, we're using the fatter data, which is the panchromatic Hubble Andromeda Treasury Triangulum Extended Region, which is kind of a forced astronomy acronym. And then we also use Chandra survey, the Chase M33 survey, which has been out for a while, but covers a really large area of M33. And then still kind of a work in progress, but I'm trying to fold in the NuSTAR M33 legacy survey, which was just published this spring. So to kind of talk about what the different multi-wavelength coverage, what we can actually do with this data. So using the HST data, we're looking in the optical, we can identify the HMXB companion star candidates. We can characterize them, try to do some type of, we don't have spectra for them. We have multi-band photometry, 6-band photometry for them, spanning near UV to near IR. And then we can also measure their age distributions. Oh, I don't know why this is animating like that. With Chandra, we're able to kind of tie the X-ray source to the optical counterpart because of its high angular resolution. And then with NuSTAR, we're allowed to constrain the compact object type, which I'll talk about a bit in just a minute. And so to kind of give you a visual on how we identify these companion star candidates, I'm showing here, these are 10 by 10 arcsecond images in the optical and the X-ray for a X-ray source in M31. So you can see on the right, you know, those kind of colored blobs are the X-ray photons coming from that source, and the circle is the Chandra measured 1 sigma positional error on that X-ray source. And then in the optical, you can see the exact same error circle overlaid on the HST footprint with that really bright blue star shown in the 1 sigma error circle. And so using color magnitude cuts, we can identify stars like these, like essentially identify them as HMXB companion star candidates, and then we put them through a series of kind of tests to vet our highest quality HMXB candidate sample. And so this is an HMXB. You don't have to remember this like phone number, but I'm going to be kind of referring to this system in a couple of the future plots. So such as this. So kind of, as I mentioned, one of the ways we identify these HMXB candidates with the HST data is using some color magnitude cuts. So you can see the optical image that I showed on the previous slide is the bottom right here. I also include the 3 sigma positional error. The left is a single band near UV image from the HST observations. And you can see that that source is also very bright in the near UV. And then you can see the cyan star on the top 2 color magnitude diagrams show its position on a UV and an optical CMD. And you can see from its position that it is a very bright main sequence star, which is likely a good candidate for an HMXB companion star. So now that we identify our companion stars, how do we actually kind of go about characterizing them? So I want to kind of lay out some of the goals for the things that we want to learn about these systems. So the first is kind of more on the identification side. We just want to obtain a large, clean sample of HMXB candidates. We want to have something that we could, maybe say something statistical about, and we want to make sure that we don't have anything in our sample that are not HMXB candidates, which I'll talk a little bit about in a second. We want to characterize them. So by that, I mean that we're going to be inferring their spectral types, so physical properties like their masses. We're going to determine their ages using these star formation history maps, and then we're going to measure the production rate, which we can kind of infer from the overall age distribution of the population. And then for the subset with hard X-ray coverage, we can constrain their compact object types, and kind of tying it back to our overall goal, which is using these population demographics that we can measure to kind of constrain our theoretical models of massive binary stellar evolution.
Can I ask about these high mass X-ray binaries, the mass transfer is unstable, right, because of the mass ratio and angular momentum considerations. How long do they last? How long are they visible as X-ray source?
That is a good question. So I would say a good question that doesn't necessarily have a good answer, I think, at this point in time. So there's a lot we kind of are still learning about the duty cycle of these X-ray binaries, which is kind of the amount of time that they spend in the visible X-ray binary phase. For my observations, we don't have time-resolved observations, so we kind of have a snapshot of the population. But it kind of depends on the type of system, so kind of what type of accretion mechanism's going on. But it can kind of, I think there can be a wide range of kind of estimates for kind of what fraction of its time it spends in the active X-ray binary phase. I mean, I think depends on the system. It can be like 10% of the time, but I think that people have measured longer, like higher fractions of active time in the X-ray binary phase.
But these are not stable, right? These are not Russell overflowing systems. So they're
just accreting from.
They're accreting either from the window, or in this case actually from the disk, right? It's accretion in the X-ray binaries. They're accreting from the disk around the B star. So they're heavily stable for a long time.
Right. Yeah.
Okay.
Wide enough.
So I'm showing here just kind of an overview. So based on, this is kind of a spoiler, I guess, on the next slide. So using spectral energy distribution fitting for the photometry we have for the companion star candidates, we can infer the likely companion star spectral types. We can't get quite as granular as the individual B0, B5 type of a thing, but we can say whether or not something is a likely O or B star, main sequence, or supergiant. And so on the left, I'm showing for the M31 population, we have about 55 HMXB candidates, and they're kind of overplotted there. And on the right, I'm showing the roughly 40 HMXB candidates that we've identified in M33. And so to talk a little bit about how we infer these physical properties to get the spectral types. So we do spectral energy distribution fitting using this tool called the Bayesian Extinction and Stellar tool, or the BEAST, which was developed in conjunction with the FAT survey. So the BEAST is actually kind of interesting. I think what we're doing with it is a little bit of a kind of edge case of what its kind of main purpose is. A lot of people are using it now to do star formation history measurements in galaxies where you can do these resolved stellar populations work. But essentially what it does is it takes in an SED of the star, it combines it with stellar models. You can create measurements of the photometric bias by injecting artificial stars and then running it through your photometry pipeline, and also models of the dust extinction, and then you get out physical properties of the star, such as its mass, temperature, luminosity, etc. So I'm showing here, this is for that same star in M31 that I showed earlier. The 4 dots there indicate its observed brightness in these 4 different bands. These are the 2 near UV and optical bands. And showing the blue line is the one for you to pay attention to, which is the full model that incorporates the stellar, dust, and the measures of photometric bias. So you can see that this is a strong fit to our data. So what we can do is we perform these fits for all of our HMXB companion star candidates, and then we can do things like throw them onto a Hertzsprung-Russell diagram to see what our population looks like. So this is for the population in M31, showing kind of the colored squares show the expected ranges for O and B main sequence and supergiant stars. The lines show isochrones of various ages. And all of the diamonds are our identified HMXB companion star candidates. The size of the point scales with its best fit radius from our SED fits, and then the opacity scales with its quality in our sample. So the most opaque ones are our best candidates based off of a series of tests I'll discuss in just a minute. And the next one is very much kind of a work in progress, but this is what we're doing right now for M33. It's kind of interesting. I need to kind of work out exactly why we have a lot of these kind of like less luminous but very red companion stars, which I think might actually just be kind of contaminants because those stars are much more common just in general in M33, so it's more likely that you would have a chance superposition in an X-ray source's 1 sigma error circles, but showing the other companion star candidates plotted over here. So,
sorry, I was just going to say, I mean, you're seeing a lot of O stars, right? And I this is very interesting because I please correct me, I'm probably wrong about this, but I thought that the even more local population, the Milky Way, the Magellanic Clouds, was completely dominated by the B stars in neutron star hemisphere binaries.
Yeah, and that's something that I'm actually a little puzzled about too, because you kind of expect it, you don't really expect like the OE HMXBs because when they're that massive, you don't really expect them all there to be that many that are kind of rotating so rapidly. So it's definitely something that I'm kind of exploring. Yeah, and it's interesting. maybe I should have put on this slide to kind of compare this inferred Hertzsprung-Russell diagram. So, remember that these are inferred properties from the SED-fits compared to where these stars actually lie on an observational color magnitude diagram. And a lot of times what happens is the SED-fits kind of infer, especially for some of these guys, observationally in a CMD, they might be kind of more over here, but then it says, oh, they're pretty reddened, really massive stars. And I think that that's something that we need to explore a little bit more. So I wanted to just say a quick word about how we determine our best HMXB candidate sample. So kind of our main goal is that we want to remove things that might be masquerading as HMXBs in our sample, which are sometimes you will have a foreground Milky Way star that is bright in the X-rays, and you might mistake that for an X-ray source in M31 or M33. And kind of one of the most pesky contaminants in our sample are background AGN, which look like bright blue point sources coincident with hard X-ray sources. And so these are things that we're trying to weed out from our sample. So there's a couple ways that we go about doing this. We compare X-ray and optical measurements of the extinction to try to make sure that we're actually looking at a thing that is in M31 or M33 and not behind the disk, which we can do by comparing the AV that we infer both from the SED-fits and then also from measurements from the local stellar populations to NH that we measure with the X-ray spectra. We also use these spectral types from the SED-fits and kind of say, both look at the shape of the SED. So sometimes if our SED looks relatively flat, our SED fitter will infer that that's actually something that just is undergoing a massive amount of dust extinction. But we also know that background AGN have relatively flat spectra in the same wavelength range that we're looking at, so that could be kind of a suspicious thing. And we look at the hardness ratios for these sources from Chandra. So we're looking for hard X-ray sources. So if something is softer, it's more likely to be a foreground star. As well as we look at the infrared colors for these sources from our HST observations. We know that foreground stars form a relatively narrow vertical sequence in IR color magnitude diagrams, and so if a source is in that kind of range, that might be suspicious. And also we're looking for sources that are in regions of these galaxies that have experienced star formation within the last 80 million years, because if they aren't, then that might just be a background AGN that's kind of randomly in that location. And so one thing that's tricky about doing this is you can't necessarily have like a one strike and you're out approach to this, because there could be kind of reasonable reasons why a high mass X-ray binary might kind of raise one of these flags. Maybe it experienced a really big kick and it's moving really fast, or maybe it does have a massive amount of extinction because it's a high mass star that is very close to its birth location. So what we try to do is we kind of employ a series of flags, and kind of if a source raises multiple flags, then we remove it from our best sample, but we try to kind of stay inclusive. So I'm going to move now to talking about how we infer these age distributions and HMXB production rates. So what we've been doing is we've been using these resolved stellar populations to determine our HMXB populations by using spatially resolved recent star formation history maps. So I'm showing you here a color magnitude diagram that is color-coded by the age of the stars in the diagram. So just to kind of give a quick overview for how we measure these star formation history maps. So the color magnitude diagram, we use color magnitude diagram fitting in the optical to determine, to measure these spatially resolved recent star formation histories. And essentially what you can say is if you see a population of stars in a region of the galaxy, you can essentially model that population, which is going to be mixed ages, as a superposition of multiple single age populations. The amount you have to weight each age to reproduce the observed population will tell you something about the star formation rate at that time. And then you can back out the star formation rate time resolved. We do this across M31 and M33 to create also spatially resolved maps. So in M31, we use star formation maps by Alexia Lewis et al. And in M33, we use spatially resolved maps. So I'm showing you here to kind of give a picture of what our maps look like. This is from M33, from the fatter data. So you can see here, each pixel, we break the galaxy down into about 2,000 individual regions, which are about 100 by 100 parsecs. And then we can measure the star formation rate kind of back to about 630 million years. We optimize these fits to focus on the recent star formation history by we essentially mask the CMD and we take out older stellar populations and we really focus on the main sequence stars for these fits. And And then for these maps, this actually isn't showing the full resolution of our star formation histories because we have 0.1 log bins for the time, but just kind of for the purpose of display to show what they look like. So the way that we use these to infer HMXB ages is, let's say we have high mass X-ray binary. We identify essentially the pixel in this galaxy that it lives in, and we can look at that region's star formation rate over time. So this is again for that kind of same star that I've been showing in the SED-fits and in the images before. So this is showing the star formation rate over the last 80 million years in this region containing this HMXB candidate. And you can see that there is like a strong peak in the star formation rate in the bin about 40 to 50 million years ago. You can essentially take this star formation rate over time. You can figure out how much stellar mass was formed in each time bin to infer essentially a probability distribution on kind of which bin this source was likely born into. And we can do that for our full population to get an age distribution, which is showing kind of how many of our HMXB candidates we expect to have been born in each of these time bins. So the dark histogram is showing for M31 population. The colored line just shows if we select an equal number of just completely random regions from the galaxy, what do we get to kind of show how much above kind of the average star formation rate we're seeing here. So in M31, we see this peak, kind of broad peak between 40 and 50 million years. We know that kind of 40 to 50 million year peak is kind of what we expect for like roughly the BE X-ray binary population. We can kind of, then we combine that with the total star formation rate in that whole area of the galaxy that we're observing over the same time span to then get what we expect, how many HMXBs we expect to have been formed per solar mass over time. And so that's, those are the plots for M31. We also, I'm showing down at the bottom left, we can integrate that over different time spans, 50, 80 million years, to get numbers that are more directly comparable with other galaxies where this has been measured, where they don't have the same time resolution on the star formation history measurements. So just for kind of comparison. M33, and I note this is still a bit of a work in progress, so showing kind of what our age distribution is looking like for the M33 population. And you can see we have kind of this younger peak. We also can then combine that with the M33's overall star formation history and back out kind of our HMXB production rate over time. I'm going to talk now about how, oh, yes.
Sorry, can I ask one more question?
Uh-huh.
How resolved is the structure in terms of star formation rate on absolute scales, like in terms of kiloparsecs locally rather than angular scales? Sorry.
Yeah, so the star formation history maps are, we basically divide them into regions that are about 100 parsecs by 100 parsecs. And that's about as granular as we can get.
Oh, I actually think that any more I think even that's maybe too granular in the sense that if you consider the fact that probably, if it's a neutron star, it got some kind of
they're moving,
kick or
yeah.
Blau kick during the explosion. It's not crazy to imagine this binary might be moving at 100 kilometers per second, right? And it may be 10 mega years, let's say, since the neutron star experienced supernova. So in that time, at 100 kilometers per second for 10 mega years, you move by a kiloparsec, right? So actually, anything that's too small a fraction of a kiloparsec, probably, if there's a lot of variation in that scale, probably artificial, because the current location of the HMXB may not be its birth location.
Yeah.
Still, it's got to stay a binary, doesn't it? So kick count too big. Pull it apart.
Absolutely, exactly. Right? Yeah. So yeah, but I think so we're talking, I think, tens to order of 100 kilometers per second. I think certainly, I mean, these are observed for in those cases where we can resolve the velocity for binaries, we know that's roughly the order of magnitude of the velocity.
Yeah, and that's something I've kind of thought about exploring. There's been work going on to kind of correlate the positions of these HMXB candidates in these galaxies with the locations of young star clusters, and you can kind of infer how fast they must have been moving roughly. So I've kind of thought about, what if we tried to kind of combine the star formation histories into like essentially, pixelate our images a little bit more.
The M33 one looks very different, right? The plot
yeah.
You went through it very quickly, sorry.
I don't want to put too much stake on it because I just made it like this past week, so I'm still kind of in the process of vetting the full population. And yeah, those plots right now are kind of plotted in log space rather than collapsing them down into linear time space. So yeah, something I'm still working on. Yes, I did show them rather quickly. Yeah. Okay, so the kind of last piece of analysis I want to talk about before going into ongoing and future work is how we fold in this hard X-ray data. So we have hard X-ray coverage not for our full sample of HMXB candidates, just in terms of the spatial coverage in these galaxies. We also expect that not every source is going to be bright enough in the hard X-rays to really be detected by NuSTAR. But for the sources that are detected by NuSTAR, we can try to start to infer what type of compact object we're looking at using the NuSTAR colors and luminosities. So on the left is a hardness intensity diagram, and on the right is a hardness ratio diagram. And the colored points are from galactic X-ray binaries of known compact object and accretion state. These observations, so each point indicates an individual observation for those sources taken by RXTE, and then it was kind of translated into the NuSTAR bands. And you can see, essentially colors clumped together. So you could essentially say, the location of a source of unknown compact object type, where it lies on this diagram might give you a hint of what type of compact object you're looking at, with the caveat of, because of, the distances to these galaxies, we do have pretty big error bars on these NuSTAR hardnesses and intensities, so you can see that there are sources that span multiple compact object types. But kind of at first order, we can kind of say, where this source lies will give us some information about what type of compact object it might be. And also keep in mind, this is kind of like a three-dimensional space, so it's kind of like the bottom panel is using, it's like if you were looking down over the top of the first panel with like an extra dimension of the two different hardness ratios to cover the hard and the medium and the soft bands. So just to clarify, I think I forgot to put that on this slide, but for the NuSTAR bands, the soft band goes from 4 to 6 keV, the medium band is 6 to 12, and then the hard band is 12 to 25 keV. So this is work that I did for the subset of our sources in M31 that had NuSTAR coverage. And this work has also been recently published in M31 by Jun Young et al., and showing kind of, what are the likely compact object types for these sources based on their hardnesses and intensities. So one thing that's kind of interesting to look into, so this is from the subset in M31, we can try to look for some trends in optical counterpart by compact object type. So on the x-axis here is the NuSTAR classification. So some of them don't have a NuSTAR classification, a lower magnetic field neutron star, a pulsar, a hard state black hole, intermediate accretion state black hole. And then on the y-axis, you can have the optical counterpart based off of the HST imaging. So for some, there isn't a clear optical counterpart, which is listed as none. You can have a galaxy that's visible in the HST imaging, a star cluster, or a point source. So this top row here, these would be our HMXB candidates, the ones with point source optical counterparts. It's kind of interesting because I don't really focus on low mass X-ray binaries that much, but you can kind of infer that a lot of these ones with no optical counterpart might be low mass X-ray binaries. We don't expect to be able to resolve the low mass stars in M31 just based on the magnitude limit of our survey, but it's something that I think could be interesting to look into. I had a couple of students working with me this summer working to create a similar diagram like this for the M33 sources. It's still a work in progress, but kind of something I'm looking into now. All right. So for the last part, I'm going to be talking about kind of some ongoing and future work directions. So I am excited about getting some optical spectroscopy of these HMXB companion star candidates, which are going to be coming this fall, taken at Keck. So kind of the main goals of that is to actually confirm these spectral classifications for our HMXB candidates. So as I described, we infer them now using the SED fitting, but we know that, for example, a BE star candidate, which is what we expect a lot of our HMXB companion stars to be, we actually don't see those hydrogen emission lines. They're not in our HST filters, which is kind of good in some ways, but can make it kind of challenging. We don't know if these are BE stars presently. And it will also be important for us to kind of make sure we've fully weeded out any non-HMXB sources in our sample, so we'll be able to kind of identify background AGN. And then also identify some good candidates for follow-up time-resolved spectroscopy, which we would look to obtain the following year, which would start to give us a chance to recover some orbital parameters and compact object mass constraints, which we don't really have the ability to do right now since we don't have these time-resolved observations. And then kind of the last bit that I wanted to talk about is, so I am currently working and excited to continue working on comparing these observations with binary population synthesis models. There's a lot that we can learn from this. So I'm currently working with Poseidon, which is a binary population synthesis code to simulate the M31 HMXB population. So we're applying observational limits on the X-ray luminosity, so trying to say like which of these sources would we actually be able to observe. And then we've been kind of focusing on the BE X-ray binary population by kind of post-processing, selecting likely BE X-ray binaries from our simulated systems using things like its rotational velocity and orbital parameters, so kind of making sure the compact object would actually come close enough to the BE star's decretion disk to accrete, and that they would be bright enough for us to observe. And we simulate these assuming the M31's star formation history as kind of a probability distribution on the binary ages in the systems. And then what we've been working on is translating these simulated systems into kind of our observational space. So I've been simulating the HST magnitudes for the companion stars in the simulated X-ray binaries. And then I've been working to apply a realistic kind of dust extinction to those so that they actually kind of look similar to what we realistically observe. And I plan to expand this analysis to include the M33 population as well. All right. So just to kind of wrap up, so I've talked a bit about the background and motivation for this work. So we know that massive binary stars are really important for a lot of reasons. Galaxy evolution, if you care about gravitational wave sources, if you just think binary stellar evolution is a really cool and interesting thing for us to learn more about. I've talked about work that I've done to study the population of high-mass X-ray binaries in M31 and M33 using overlapping multi-wavelength observations from HST, Chandra, and NuSTAR, with which we can start to constrain the companion star characteristics, these age distributions and production rates for the high-mass X-ray binary populations in those galaxies, and infer the compact object types for the subset of our sources for which we have this hard X-ray coverage. And then lastly, I've talked about some ongoing and future work, so kind of looking at diving deeper into the classifications of these companion stars by obtaining optical spectroscopy for them. And I'm really excited to kind of continue working with the comparison between this observational population demographics that we have and comparing that to theoretical populations that we can produce with binary population synthesis models. So I will pause here and take questions. Thank you. Yeah, I'm excited we're finally going to be getting that, because I feel like for so long I've been looking at these like Hertzsprung-Russell diagrams, and I'm always kind of like, ooh, some of these stars up here, I'm like, is that really realistic that they're this luminous? But I think it'll be really great to kind of be able to
pin them down.
I actually had a question on that. So you're correcting for the dust extinction on an object-by-object basis, are you?
In what sense you mean? Like on the SED fitting?
Yeah.
Yes,
So
it's like a free parameter in our fits.
So the amount of dust can be different depending on the object, but like if you do like a spatial distribution of dust, would it be like really like messy, or do you have like smooth distribution of extinction?
Oh yeah, that's a great question. So we do kind of, so one of the things that we do when we're trying to kind of vet our sources is figuring out whether the dust we do on a source-by-source basis agrees with kind of the galaxy-wide distribution of dust that we expect to see. So in M31, we have really detailed dust maps that were created as part of the FAT survey. So using like color magnitude diagram fitting of all of the stars kind of within the different field of view. And then in M33, we don't have quite as great of maps yet. The fatter survey just like came out like a year ago. So nobody has done that quite yet. But in doing the star formation history measurements, I did fit for the dust extinction. So both like AV, so kind of dust, line of sight, and then DAV, which is local extinction in that region of the galaxy. So we did kind of check to see if the dust that we're inferring source by source kind of makes sense with what is going on locally in that part of the galaxy. And you see that for the galaxy-wide, the dust, you can kind of see when you, I don't think I have a plot of it in this slide deck, but you can see the shape of the spiral arms. Yeah.
Sorry, if I could follow up on that, do you try that? Do you try to do the extinction fitting just for the X-ray sources, or do you also do it for random similar stars in the same field? Because I was wondering if you see a significant difference between the two.
Yeah.
Right? If you take a similar sample, okay, otherwise, sort of similar looking stars that just nearby that are not X-ray sources, right? Okay.
Right.
Conceivably, if you see that you need very different corrections, it could tell you one of two things, right? Either that the X-ray sources are somehow, very different,
yeah,
which is, very plausible because
right,
they, maybe there was some loss of material from
yeah,
etc. Or it could tell you that they're just genuinely different stars, and by trying to fit them onto sort of something that looks like a normal
star, yeah,
star, you're forced to have a weird extinction model.
I have not tried that, but that's a really great idea. Yeah. Cool. Yeah, especially because we would expect, like, for the BE stars, they often have kind of like a IR excess, which could kind of make our fits. We actually, so in our SED fits, we don't really include the two near IR bands, just because, not so much because we're worried about that for the BE stars, but because there's just such a high density of stars that are bright at near IR wavelengths in those galaxies that there's a lot more kind of crowding and issues with our photometry. But yeah, that's a great idea.
Is getting a time series hopeless, or is it like, can you get a light curves of any of these sources?
So for the M33 sources, we do have some time series X-ray observations. So yeah, we recently, I think the observations, they kind of came in over the last couple of years. I think we have about 5 or 6. They're much less deep. They're only like 25 kiloseconds, which is a lot less deep than like the deep survey data. So we aren't going to be able to see all of our sources, but that is something that, yeah, we have a student working on that right now, trying to see some variability information.
Are there any optical?
So yes and no. So I'm interested, one thing I've been thinking about is how to use some of our, some of this kind of massive all-sky survey type data that is coming out now. So Gaia recently released a lot of data for M31, which I'm excited to look into, including some time-resolved, like low-res spectroscopy. I don't know if, I'm not exactly sure what the magnitude limits are on that, so if all of our sources would be observable in that or just the brightest. So I'm interested in that, and I'm planning to start this fall trying to look into doing some follow-up with ZTF as well, since there's also coverage of M31 and M33 there too.
Any periodicity would really help
yeah,
determine final properties.
Yeah, and I think that's something I'm excited about. I want to try to do that, I think, in the next year, because I think that would also inform, if we can see some rough periodicity in those data, that would inform, which sources would be good for the more, the optical time-resolved optical spectroscopy. So we could really target the ones that seem to be.
What are the typical orbital periods of these things?
So for like the BE stars, I think, and someone else who can correct me if I'm wrong, I think it's like 10 to 100-ish days is what we expect to see.
Milky Way, I remember from a long time ago, a pulsar with a BE star coming in on a very eccentric orbit. There's probably many of them known by now, 0.8 eccentricity or something. You see it light up in the X-ray when it comes through periastral. So beautiful.
Mm-hmm.
There's even claims of a warping disk.
Yeah.
So every time it comes in, it's at a different time.
Yeah.
Actually wondering, given the orbital period, which is reasonably long, at least for some of these, maybe even LSST observations could be useful, right? Because you're getting a snapshot only every few days, but of course the sensitivity is very high, right? And
yeah.
so that might be enough to see some kind of variability in the optical, if there is any variability. So you could actually see periodicity from just discrete measurements taken every 3 days if your orbital period is 30 days, right?
Right.
Let's thank our speaker again.